All right, so previously we talked about Riemannian manifolds, it's like, and the associated Levi-Civita connection. And so now we're going to revisit this issue of dual connections, dual affine connections, which arise as a consequence of information geometry. Okay, so these are dual connections. So the Levi-Civita connection is the only sort of affine connection that is torsion-free and metric compatible. And so what that means, in particular, with regards to metric compatible, is that it preserves the metric under parallel transport. Okay, so what that means basically is that if you have two tangent vectors, say at some initial point, and you take its Riemannian inner product, that gives you a certain value. It's like, and if instead it's like you were to parallel transport that pair of vectors via the Levi-Civita connection, and then take their Riemannian inner product anywhere along that curve, right? That would give you the same number. Okay, so that's what we mean by metric compatible. And you know, it's like previously we had sort of alluded to this idea that there was another way of you know, generalizing this notion of metric compatibility, because you have two vectors, right? So nothing, it's like, requires you to parallel transport those two vectors with the same affine connection. And so one can ask, well, what happens if you have two different affine connections and you parallel transport, it's like that pair of vectors, one of each of those affine connections. Okay, so now we consider a pair of connections of sort of symmetric affine connections. Let's call that gamma and gamma star, right? And we denote their the associated parallel transport by pi and pi star, okay, respectively. So these sort of these affine connections are dually coupled. Right, when the following holds, right, that if you take the inner product between two vectors, right, that's equal to the parallel transport of the first vector by the first affine connection, and the second vector by this dual affine connection. Okay. All right. So that obviously generalizes, it's like the notion of metric compatibility, it's like which we have, it's like with the Levi-Civita connection, all right? And so there's a sense in which the Levi-Civita connection is dual respect to itself, okay? So yeah, so when the two connections same, right, this reduces to the usual notion of metric compatibility. Okay, and there's a sense again in which the Levi-Civita connection is self-dual. Right. So you can ask, is there some way to characterize it's like affine connections which are dual to each other, right? Okay, so let's try to do this. Okay, so is there a way to characterize sort of dual connections? Well, besides the obvious statement like this, okay. So let's consider two basis vectors. Okay, so E tilde I, E tilde J at the point cos C plus D cos C. We want to parallel transport them back to cos C using two connections. Right, so let's see what you get. It's like when you do this. And of course, it's like this is just expressed in terms of the connection coefficients, right? Just by definition, if you will. Okay. So you have EI plus DEI, right, is equal to EI plus gamma, KI J, EJ D cos CJ, D cos CK, I'm sorry. Okay, and then EJ plus DEJ is equal to EJ plus gamma star KJI EI D cos CK. All right, we changed the index because we've parallel transported two vectors, one with a subscript I and one with a subscript j, right? So that's, yes, all right. And let me just call it, sorry, D star EJ. Okay, and then we use the fact that the inner product is preserved, right? So from the preservation of the inner product, right, we have the following, that EI tilde, EJ tilde at the point cos C plus D cos C, right, is equal by definition to EI plus D EI, EJ plus D star EJ paired at the point cos C. Right, so these are tangent vectors. It's like at cos C plus D cos C, they're being parallel transported back to it's like the tangent space at c. All right, and so we have this relationship. Okay, so we can write down what these are. Okay, so we also have to do something about the metric, right? So we also have that. Actually, no, from this relationship we have that Gij at d at c plus d c right is equal to Gij at c plus then the cross terms, right? So d ei ej plus ei d star ej at c. Right, and then we're ignoring it's like the term it's like which involves it's like two infinitesimals. It's like because they're very small, right? So where we ignore sort of things which are sort of terms at a higher order. In DE. All right. Okay. So so what you can and these it's like obviously are related to the connection coefficients, right? If you recall. So what remains to do is to look at this thing on the left-hand side and then do a Taylor expansion. It's like on the left-hand side. Okay, and then what will happen then is that obviously you get a Gij at c term plus some first order variation. It's like in this thing, and that's going to be equal to those sort of connection terms. Okay, so by Taylor expanding on the left hand side, and again ignoring higher order terms, right, then what we get is that at component level, the partial respect to I of Gjk is equal to gamma ijk plus gamma star ikj. And then, as you might expect, the self-dual case is when, you know, it's like these two are the same, right? All right. So what can happen then is that I can rewrite this in terms of covariant derivatives, right? As z acting on xy, the inner product between xy is equal to nabla z xy plus x nabla z star y, where x, y, and z are vector fields. And to see sort of more clearly, it's like how this is equivalent to this statement, right? You can consider specific choices of x, y, and z, right? So we can verify this by considering x is EI, y is EJ, z is k, right? And what happens when you do that is that EI paired with EJ, EK, right? This is the, you can check that this is basically the directional derivative in the ith direction, right, of the inner product between EJ and EK, which pulls up this metric term, GIJ, right? So hopefully you can see how this is related to this expression. Okay, and you can do something similar. It's like with these things, right, and these terms, that this is equal to nabla EI, EJ, EK plus, it's like EJ nabla star EI, EK. Right, which again, it's like once you've used the fact that these are basically pulling out the coefficients, it's like in the connection, it's like coefficients, right? You get exactly this relationship. I'm sorry, not this relationship here, right? Okay. All right. So now you have these two. It's like a pair of dual connection forms. So let's consider what the average of this is. Okay. So the average of the two dual connections is given by gamma ijk 0, which is 1/2 gamma ijk plus gamma star ijk. Okay. And then there's an associated covariant derivative to this. I should have said that these were the covariant derivatives associated with the connections, right? So anyway, so this is the average, and then there's a corresponding covariant derivative as well, right? So the associated covariant derivative is as follows, right? So it's nabla 0 is 1/2 nabla plus nabla star. Okay. So from this, right, we see that nabla 0 satisfies the condition for the Levi-Civita connection, well, for the covariant derivative associated Levi-Civita connection. And indeed, it's like that, this average of the dual connections is the Levi-Civita connection. Okay. And it's like as you might expect, if you had this self-duality, it's like that the average of those two things would be the same as it was before. So that's consistent with our intuition. Okay, all right. So with that in mind, you know that the average, right, is can be expressed. It's like in terms of the Levi-Civita connection. So you might ask, well, how do you, then you can compute. It's like the difference between the one of the connections. It's like with the Levi-Civita connection. Okay. So. All right, so let us define a new tensor, T ijk, which is the difference, so it's like between that pair of dual affine connections. So gamma star ijk minus gamma ijk. Right, so with that definition, then you can write down the dual connections in terms of the Levi-Civita connection. It's like in this new, it's like tensor, right? So then the affine, sort of the dual connections can be written as follows. And let me state a theorem. It's like about this this object. So this is going to turn out to be a symmetric tensor. So the theorem is that when gamma and gamma star are dual affine connections, which again, if you recall, implies that if you parallel transport, it's like one vector by one of the connections and another vector by the other connection, then their Riemannian inner product is constant, right? That's sort of, again, generalizes the notion of metric compatibility. It's like two sort of pairs of connections, okay? So then T is a symmetric tensor sort of given by the following. Okay. So if you take the covariant derivative basically of the metric, right, then you get, with respect to the first one, then you get this tensor. And if you take the dual, you take the covariant derivative with respect to this dual connection, you get, well, this is the inverted metric, right? You get minus T ijk. Okay. All right. So I'm not going to prove this. It's like, but this is the proof. This is discussed in the book. All right, and it's really sort of a calculation, if you will. Okay. So in some parts of the literature, this T is referred to as the skewness tensor, um, but that's a little bit confusing because as you sort of state in this theorem, this T actually is a symmetric tensor, and skewness sort of oftentimes implies antisymmetric. So that's why the book refrains from referring to this as the skewness tensor. All right. Okay. And let me sort of just say further that one way it's like in which dual sort of connections arise, it's like in the context of information geometry, is that if you have one of these divergence functions, which if you recall in general, it's like it's not symmetric under interchange, it's like with the arguments, right? Then when you take, when you evaluate, derivatives, it's like of that and evaluate it along the diagonal, right? Then you end up getting a sort of connection coefficients and dual connection coefficients, which are metric compatible in this sort of extended dual sense. Okay, so let me just stop here for now.